Hello, it's again me. Today I would like to speak about network sniffers, and the basic principle of implementing a network sniffer is manipulating with the raw socket, then receiving all the data which you can take through a port or from an IP address, then unpack the actual IP packet, and then parse all the payloads of the IP packet, which contains the next layer, the transport layer packets like UDP, TCP, ICMP, RP, and others. Okay, what are the basic principles of a network sniffer? The information you sniff should be human readable, of course, nicely structured. So, what does an IP header contain? Actually, when defining a raw socket, we should take into account that the host, actually the IP address, can be already in use. So this is why we should declare some special options on sockets. One of them is including all the headers on the IP, and the second one is receiving all the packets. Also, in order to run the sniffer on the same machine, we can also define the reuse address if we want to listen to a specific port here. When define the 0 port, we listen all the information that goes through a network adapter. So we define a raw socket using the IP protocol and actually starting to listen. While true, we receive all the information, and then the main idea is that we receive some binary data, a lot of binary data. We don't know what to do with it, so actually we have to make some manipulations. We take the first 20 bytes of the data, which actually is the IP header. How do we know it? There is a strong RFC defined that the IP header length shouldn't be more than 20 bytes, and all the information we need is stored there. Now, in this laboratory work we actually use the IP version 4 packet, mainly because the IP version 6 packet has some different structure, and we shouldn't work for now with that. The program was written to IP version 4 packets. So we split the information, first 20 bytes and assign it to an IP header. Then using the unpack function from the structure we imported, from the structure library we imported, we unpack all the bytes we need from a binary data in a package. Actually, it is a list which is named IP header unpacked. So the unpack function is not very hard to understand. Unpack Python. There is a definition of each field we want to unpack from the struct lib. So here it is, how it's shown. Actually, we unpack it in different sizes. B means unsigned. B means a structure of size of 1 byte. H is unsigned short, it's a size of 2 bytes. Long is 4 bytes. String is not defined because we input which dimension we want to give it, and so on. So we unpack our IP header in such a way that it is BBHHH, BBH, and 4 bytes of strings. How do you know how to unpack the packet? Actually, it's very easy to solve this trouble, mainly because in the structure of an IP packet there are defined all the sizes of each field. So each set of bytes we unpack in using the unpack function defines actually a special field in the IP header, which is shown in this table. After we unpacked all the IP header, all the 20 bytes we received, we should make some manipulations on them. So the version of the IP packet and the IP packet header length are packed in IP header unpacked 0, which is the first structure unpacked. In order to receive all the information we need, the actual version and the header length, we should do some binary manipulations. To receive the version, we take the structure and shift it right 4 times. This gives us a simple answer, which actually is when having a structure, for example 111000, 8 bytes unpacked, and after shifting it 4 times, we receive such a string: 4 bytes of zeros and 4 bytes of ones. Then we read only these 4 bytes, and actually it is the information stored in that field. So in the version field, then in this way we receive the version. Then we should manipulate also that structure, version and IP header length structure of 8 bytes in order to receive the IP header length. How do you do it? We make a logical AND with FFF, which actually is nulling all the first bytes, which is actually switching these 4 bytes and these 4 bytes. And after performing this logical AND, yes, I suppose, we can throw out first 4 bytes and just use last 4 bytes, which would be our data. In case that some data is stored there, some data is in the first bytes, after flipping actually with the logical FFF, it nulls. Yes. So yes, also IP header length we should multiply it by 4 in order to receive the actual size in bytes, because it's stored in 4 byte words, the actual size. So next we should unpack the information stored in the IP header unpacked structure list within index 1, which is the second field, which is type of service field, and in such a way we like unpack and represent all the structures we have, reaching to the total length of the packet of the packet total length, identification. We can reach any field from using a special unpack sequence. Fragmented offset, time to leave, which protocol we use, header checksum, and all of these are unpacked here. Identification number, time to leave, protocol, head checksum, source address, and destination address. Also, in order to receive a nice looking source address and destination address, we should convert the unpacked structure and convert it actually to a 4-digit string standard representation of an IP address. So then we nicely format all the information for printing out, like doing new lines, headers, adding all the information converted to strings. And then comes the interesting part. Identifying the protocol field we received and unpacked and received converted, we can unpack next types of protocols from the network stack, from the transport layer. Receiving the number 6, actually it is the TCP protocol identification. We can unpack it also. From the IP header length field, which we found, we select passing the actual IP header length and adding 20 bytes. We are splitting out the TCP header, knowing that the TCP header length is 20 bytes. Then unpacking the TCP header also with the special sequence of structure, with the special sequence splitting it in structures, separate structures in a list. We can also parse it, each field separately, identifying the source port, the destination port, sequence number, acknowledgement, TCP length, also TCP checksum, urgency of packet, and basically it can be all information we need. And as I didn't mention, the data offset reserved, special field reserved for data offset. So then we format this information nicely. Also, the data of the TCP length is the data offset shifted for, yes, as we manipulated the field higher in the IP version, the field was like 8 bytes and we had to shift it 4 times in order to receive the necessary information. As well, we received in such a way the TCP header length. Then we actually solved like the length in bytes of the header, because it's also the value of the TCP header length. It's 4-byte words. Yes, are the 4-byte words. In order to find out what is the header size, we had to take the IP header length, add it to the TCP header length and multiply it by 4, and then subtract it from the length of the packet we received, this header size, which is the IP header size and TCP header size, in order to reach the payload of the packet. and from that size till the end of the packet there was all the payload, the data, the actual data. It has some special representation. It can be different symbols, and if we just want to see the actual binary representation, we can write it like repr of the data, and we'll receive like binary Python representation. So the next packet we can unpack is the 17 identification, like identifying the UDP packet, which number is 17 from the protocol field of the IP header. Also, we have to do some simple manipulations like UDP packet length, UDP header counting. UDP header length is actually 8 bytes long. When packed in such a way, UDP header starts from the actual packet, the IP header length, and the UDP header length plus 8 bytes. Then we unpack the UDP header, obtaining the source port, destination port, length port, and checksum. In the previous lab, it was presented the table for these fields. Then printing them out nicely, calculating also the header size, which in this case is the IP header length and UDP header length, subtracting it from the length of the packet, and all the rest of information is the actual data sent through the UDP packet. Also in such a way, if the identification if the number in the protocol field is 1, it means it is an ICMP packet. Its structure you can find on Wikipedia. It's not very long, it's simple. It's very simple. ICMP, it should be somewhere here. Okay, we can search it for like ICMP. Here it is, Internet Control Message Protocol. It has simple structure, like you see here, type, code, checksum, and rest of header, which is type, ICMP type specified, subtype given, checksum, and rest of the header. So we also parse it, unpack the information, calculating the headers where the actual header is stored, taking the necessary fields from the unpacked structure, the type, the code, the checksum, calculating the header size, which is the IP header length and ICMP header length, subtracting it, and receiving the actual data sent through that packet. And anything else we receive, these are different types of protocols which we didn't parse. Also, we can verify tons and tons of protocols. It's not a big problem. And then we should disable the promiscuous mode, which on closing the application we shouldn't receive all the information, because actually not only on closing and also on using it, when we receive the packet, parse it, we shouldn't keep this option on, mainly because there are different security applications like antiviruses, firewalls, and tons of sniffer detectors. And if you try to use all the time on receive all option launched, it can spot you and then just kill your process in order you to not receive all the packets sent through the network. Yes, and that's all. Now I can show you how the program works actually. And I've written several versions. There is only Windows TCP, Unix version, which differs only with setting these options is something different. In Unix we set the socket raw, and also we can use the IP protocol also raw, which gives us a possibility to also receive the MAC address. So we can launch the application. As you see, we start receiving packets, lots of packets, different packets. If the representation of the packets in console shows like /A, it makes a beep sound. I can press pause and let's analyze a packet. So here it is the IP version, which is version 4, IP header length, type of service, total length, identification number, time to leave, protocol 17, which is the UDP protocol. No, 17. Yes, 17 is the UDP protocol. I was right. Then the destination source, the source address, destination address, header checksum, and then parsing the UDP packet. It's the source port, destination port length, and checksum, and the data sent through this datagram. Also, we can try to find, maybe we can manage to find another protocol, or we can generate. Oh yes, we have another protocol, which is the protocol 6, which is the TCP packet. It has next field source port, destination port, sequence number, acknowledgement, header length, checksum, and if it's urgent, it's a flag set. Flag, if it's set to 1, it's urgent. If it's set to 0, it isn't very urgent. Yes, and the actual data, the payload. Basically, that's all. What could be further? Don't know. Implementations. We can also like parse all the flags we receive, and so on and so forth. Thank you very much. That's all.